Akshay. Okay, let's begin. So in the last class we started to look at the issue of nonlinearity. So we essentially saw that all the MOSFETs are nonlinear, so any circuit you make with MOSFETs will also be nonlinear, and the effect of nonlinearity is that it kind of distorts your incoming signal. Although the distortion might not be apparent when you look at time domain, it will be very prominent if you look at the frequency domain spectrum. And in particular we saw that if I have a fully differential circuit like our op amp, is there anything you can comment about the nonlinearity? In fully differential circuits, the even harmonics completely get cancelled, so you are left only with odd nonlinearity. So I'll say no even order nonlinearities, and this is assuming that the two half circuits are identical. There is no mismatch. If there is no mismatch, then you will not see any second order nonlinearity. And towards the end, we also looked at a way in which you can get a linear GM, and that gives rise to the source degenerated structure. So again, the idea is to make sure that your V to I conversion depends on a resistor alone. So instead of applying the input directly, you kind of buffer it and feed it to the resistor. So if this is the resistor R, what is the short circuit GM approximately? It's 1 by R, right? Because ideally source follower, this will also be V in, the current is V in by R, and that's what determines the small signal current. And then we saw how to use this and make a differential amplifier. We saw two different variants, and we finally noted that here there is an inherent negative feedback happening, because if I go and increase the gate voltage, initially the drain current tends to increase, but if the drain current increases, the source voltage also increases, so the effective VGS drops, so the current also reduces. So there is an inherent negative feedback action happening here, and that is what is making sure that although your input signal is swinging a lot, the actual VGS that the MOSFET processes is very small. So the MOSFET is still operating in its small signal regime, so things are linear, right? So today we'll see if this is indeed a general property of negative feedback, or this is particular to the circuit. Okay. So for that, let's take a generic negative feedback loop. So let us say I have an amplifier which is nonlinear. So let us say the coefficients are alpha 1, alpha 2, alpha 3, etc. I enclose it in a negative feedback loop like this with a feedback factor beta. Okay. Say this is input and output. Now since the amplifier here is nonlinear, I know that the output will also be a nonlinear function of the input. So I can write it as k1 times V in plus some k2 times V in square, etc. So our goal is to find what are these final nonlinear coefficients and compare them with alpha. Right? In open loop, if you just take the amplifier alone, the nonlinearity coefficients are alpha 2, alpha 3, etc. So you want to see, after we enclose it in negative feedback, what is the final nonlinearity. Okay, that is the goal. So again, you can solve it in a brute force way. So if I call this as the error signal VE, what is the error signal VE? V in minus beta V out, fine. And I know V out, so I'll write it like that. So beta times k1 times V in plus k2 times V in square, and so on. Okay. Now I found VE. What is the relation between V out and VE? Yeah, I mean VE is a signal fed to the nonlinear amplifier. The coefficients are this. So what is V out? Yeah, alpha 1 times VE plus alpha 2 VE square, and so on. I'll write only two terms for simplicity. Okay. So my final goal is to find these coefficients k1, k2, k3. So I'll try to replace both left hand side and right hand side with these things. So I know what is V out. V out is k1 V in plus k2 V in square plus blah blah blah. This is equal to alpha 1 times the error signal. The error signal is this. So I'll just replace it. So I'll actually simplify this slightly. So here I'll take the V in term together. So I'll have V in into 1 minus beta k1 plus k2 V in square. Okay. So if I replace it, I'll have 1 minus beta k1 times V in plus k2 V in square plus so on, plus alpha 2 times this entire thing square plus so on. Okay, I'll not write. Sorry? Beta k1, right? Oh, sorry. Okay, sorry. Oh, thank you. Yeah. Okay, got it. Yeah, understood. Yeah. So this is minus beta times, yeah, correct, thanks. K2 V in square plus 1. Yeah, you're right. So this also I write it. Minus beta times K2 V in square and so on. Okay. So now how will I solve? I mean, again, remember the goal is to find K1, K2, K3. So how do you propose I find? This is the equation. Okay. I guess you know we can compare the coefficients of V in square and so on and equate it. So you can do that. And by the way, why can you do that? I mean, why can you equate the coefficients of V in square on either sides? I mean, that is, if I have, let us say, I know x plus y is k1 times x plus k2 times y, you will not say, k1 is 1, k2 is 1, right? So why do you do that here? What? Okay. So, I mean, it's not completely. We have never questioned it, okay? I mean, okay. I mean, the question is why can you equate the coefficients of V in square, etc. here? Correct. So, I mean, again, the counter example is if I have a system like this, x plus y is equal to, I don't know, k1 x plus k2 y. It's not like you will say k1 is 1, k2 is 1, right? Yeah, I mean, see, the thing is, have you heard of basis functions? Anyone? So it turns out, I mean, if you have a polynomial space, polynomial space f of x, the basis functions are these things. Okay. So what it means is, you cannot get, let us say, x square by doing any linear operations on other basis functions, right? Basically, these are all linearly independent. If they are linearly independent, by doing any linear operation, you cannot get one from the other, right? So that is why you can actually equate it. It's a linear operation that is being done. There is no way in which you can get V in square by doing a linear operation on V in cube, etc. So which guarantees that the two sides coefficients have to match, right? I mean basically Fourier series, Fourier transform is also that, right? In Fourier transform, your basis functions are e power j omega t, right? Even e power j omega t is for different values of omega, it's linearly independent. You cannot get one omega from another omega. So even if you have a case where some e power j omega 1t plus e power j omega 2t, if you find it to be equal to k1 times e power j omega 1t, I can safely say k1 is 1, k2 0. I mean, what I'm saying is, yeah.
It is same like for calculating k1, you have to observe it for a very small value of V.
I mean, that is that is an approximate thing. But if you want to find it exactly, you have to take everything, right? Yeah, so you can do it in you can equate the powers of V in square, etc. on either sides. I'll give it as an assignment, or let's do only for k1. Intuitively, what do you think k1 will be? K1 will be? Yeah, why? That is a linear gain, and you can quickly check it. Equate k1. Powers of Vn will be k1 and this. You solve it, you will get this as k1. That shouldn't be surprising because if the amplifier were truly linear, this is what you will get. right? And similarly, if you actually, I'll give that as an assignment, you work out. I don't want to solve it here. K2, you'll find it to be, I think, some alpha 2 by 1 plus alpha 1 beta whole cube. Similarly, K3, you'll find it to be something by whole power 4. So this is what you will get, but let's see what's happening. So earlier, the second order nonlinear coefficient was just alpha 2. Now it has become alpha 2 by 1 plus alpha 1 beta whole cube. So has it become better or worse? Better, right? And in fact, if I have a large alpha 1 beta, the nonlinearity is also reduced a lot, right? And what is alpha 1 beta here? Yeah, remember, alpha 1 is the linear gain, alpha 1 beta is the linear loop gain, right? So the result seems to suggest that if I have a large enough loop gain, then the nonlinearity also reduces, right? That's what our analysis seems to suggest. So let's try to make some sense out of this. So let me actually try to see if I can copy this. So let us say I have a case where my loop gain, which is alpha 1 beta, tends to infinity. Okay. Then what can you say about the error signal? This guy? As to 10 to 0, again, it's negative feedback. Things are all stable. All voltages are finite. So which means this guy has to 10 to 0. And what is VE? VE in terms of V in and V out. Yeah, V in minus beta V out. So this will exactly go to 0. So V out is 1 by beta V, right? So if you have an infinitely large loop gain, then irrespective of the nonlinearity of your amplifier, the output will be a nice linear copy of the input, no questions asked. Okay. And again, that's happening because if you have a large enough loop gain, the error signal reduces. So although the input signal is swinging a lot, the actual signal that is exciting your nonlinear system is this error signal, and that's really small. So which means things will be more linear. Okay. So you can also understand it in from a different perspective. So let me actually copy it once again. So let us say this is some nonlinearity f. Okay. So I can view what's happening in the system as follows. So this system is basically taking my input signal V in, and first it is generating an error signal VE, right? Here is this, and then this error signal VE is converted to my output, right? So you guys know what is the relation between V out and VE. What is that? It is a nonlinear operation done on VE, f of VE, right? So we know the relation from here to here. Let's try to find the relation from V in to VE. Okay. So if I write VE, again VE is V in minus beta V out, and that is basically V in minus beta times f of VE. So I'll just take VE terms together. So VE plus beta f of VE is V. Okay, I've just taken this term here. Okay. So now tell me, if I have a large loop gain here, so how can I approximate this as? I mean, remember that f of E is basically some alpha 1 VE plus alpha 2 VE square and so on. This is plus VE. What I'm saying is I'll have a large alpha 1 beta, right? So compared to this guy, this term is going to be really large. So I can kind of ignore this. Okay. So I can approximately say that my beta times f of VE is okay. So what is the relation between VE and V in? From here, can you tell what is VE? Yeah, 1 by beta times f inverse of V in, right? Betas are okay, yeah, okay. Yeah, okay, fine. You're right, yeah. Yeah, strictly speaking, I think that is correct. F inverse of by beta. Okay. So basically now if I try to model this, what's happening is the following. I have the error signal. The error signal is first, sorry, the input signal. Input signal is first getting converted to an error signal, and that relation is some f inverse of something, right? Or otherwise, to be very correct, my V in is first getting scaled by beta, right? V in by beta, and V in by beta is getting passed through f inverse, right? And this is my error signal VE, and from VE I am getting V out. And how am I getting V out from VE? Here the relation is f, right? So now we can clearly see this negative feedback loop operates in such a way that it first generates an error signal VE, and that error signal VE is related to my input through the inverse nonlinear function, right? So which means now if I follow it up with my actual nonlinear block, these two kind of cancel, so you end up with a purely linear operation. Okay, and again this will exactly cancel only if this equation were true, but this is only approximate because we kind of neglected this term, right? And if this can be completely this can be neglected fully only if alpha 1 beta is extremely large. If alpha 1 beta tends to infinity, then this guy doesn't play any role. So we can, this equation is true, then there will be no nonlinearity. Is clear? So typically we say that negative feedback pre-distorts the input . So basically negative feedback loop, it's a smart thing. It knows that whatever amplifier you are going to design is going to be terribly nonlinear. So it will somehow understand the nonlinear relation and put an inverse nonlinearity upfront so that overall things will become linear. Right? And this pre-distortion is kind of a common thing that is done a lot of times. So if you know that your system is going to be nonlinear, to correct for the nonlinearity, one option is this: you estimate what is the nonlinear relation, and you can add an inverse nonlinear function before or after this. That you can do typically to kind of counter, counter nonlinearity. But negative feedback loop does it free for you. Cool. So this is clear. Let's see. So there's one other interesting thing here. So here let us say I have a infinitely large loop gain, right? And instead let us say I have a feedback factor, there is a nonlinearity. And let us say that nonlinear relation is some g, right? Now can you tell me what will be the relation between V in and V out? Can you take a guess? This has infinite gain. It is nonlinear, but let us say the linear gain is infinite. And the feedback factor, in the feedback I have a nonlinear function inserted. Now can you try to guess what V out will be in terms of V in? Right, yeah. So basically, see again, how do you proceed? What is the error signal now? Error signal will go to 0, right? And my error signal is V in minus. This is the error signal. This is 0. So what is V out? The inverse of V. So this is another nice thing. You can use negative feedback to generate inverse nonlinearity. Okay. And again, it should not be surprising, because if let us say this were a linear gain beta, what is the relation between V in and V out? It's 1 by beta, right? I mean, it's a linear scalar, it's 1 by beta. If it's an actual function, it's going to be the inverse function. So this is one clean way to get kind of nonlinear, inverse nonlinearity, right? And again, this is all happening because we have an infinite loop gain, right? And that is why we strive to make an op amp with as large a gain as possible, right? Because if your gain is very large, even if your op amp is nonlinear, the moment you use it in a negative feedback loop, which is where you want it to be used, the nonlinearity will be suppressed, right? Because as we saw, the nonlinear coefficients in closed loop, they get scaled by the loop gain. Okay. And yeah, I mean, in practice, if you want, I'm saying, I mean, let us say sometimes you know that your system is nonlinear for some other system. Let us say you are making some system which is nonlinear, right? Let us say you want to generate an inverse nonlinear function to cancel it. You can do it.
Instead of that, I will use an ideal op amp there in the main.
No, let us say that are some other things that results in nonlinearity, right? I'm just giving an example. In fact, I mean, olden times people used to make a V out versus V in, which is related through log and all, right? Because this was happening because if you have a diode or a BJT, the IV relation is exponential. If you put it in feedback, that inverts and gets you log. Because let's not digress. Right? I'm just saying this is a feature. If you want, use it. If you don't want, it's okay. Yeah, like I told, that's why you want to have infinite gain. But in practice, of course, you can't get infinite gain across all frequencies. So is there some block that you know that has infinite gain at least at one frequency? No, I mean, in practice you can't make an infinite gain across all frequencies. But do you know a block which has infinite gain at least one frequency? Huh? I mean, something that has infinite gain at one frequency. I mean, if need to have, yeah, LC tank, but a simpler version. LC tank is correct. I'm not saying it's incorrect, but can you down convert it to DC? If you have an integrator, what is the gain at DC? Infinity, right? So that is why in a lot of systems you will find that this is a recurring theme. You have an integrator, you want to make something equal to something else, you subtract two quantities V1, V2, feed it to an integrator, do something, put it in negative feedback. Now the integrator, as you know, has infinite gain at DC, right? So which means if I look at the error signal at DC, what can you say about that? Error signal at DC will be exactly 0. So which means my DC V in will be equal to DC V2. So that's why this will be a recurring template in a lot of systems, right? So I mean, if you are taking E69AG, you would have noticed DLL, PLL, everything follows similar template. You have an integrator, you put things and do it. I mean, in fact, I mean, how many of you have taken any course on regression, machine learning or something? No? Only one. Okay. You have gradient descent. Have you? So actually speaking, gradient descent, you can actually model it like this. I mean, not go there, but gradient descent, everything kind of depends on the fact that you have an integrator and you have something added here. And the fact that the integrator has infinite DC gain is what will make this go to 0. So these two will become equal. Because there you kind of repeatedly add, repeated addition is integration, right? So yeah, so integrator is one, powerful thing that is kind of making our world stable. Cool. So yeah, one other thing is, so let us say here, the forward amplifier has, let us say, only till second order nonlinearity. Okay.
So what was the use of having an infinite gain at one frequency?
Because you want to make sure the error at DC is at least 0. You can't make infinite gain across all frequencies, right? I mean, even your OTA, it's an integrator, right? Because for an ideal OTA, the output resistance is infinity, right? So this is going to push out a current GMV in, and you will have a capacitor. So the output voltage is what? If I write V out of S, what is that? Yeah, GMV in by SC, right? It's an integrator, right? Whatever op amp you are making, You can't get infinite gain across all frequencies, so try to make at least at DC, right? And that is good enough because at least at low frequencies you get 0 error.
At least you are sure that there is no effect of non-linearity at DC.
Yeah. At low frequencies, non-linearity will not be there. But again, the idea of having integrator is you want to have 0 steady state error at least DC. Right. Okay. Yeah. So let us say I take this same negative feedback loop where the forward amplifier has only till second order non-linearity. Now let us say I feed in a sinusoid here at a frequency f0. What are the sinusoidal frequency components I'll observe at the output? Okay, f0. Okay, DC f0 to f0. That's all. Okay, so let's see if this is the case. What are the sinusoidal frequencies that will be present in VE? Huh? I'll have same thing, right? I mean, of course, f0 will be small, but some component of f0 is there. So now this is getting processed here. What will it generate? I mean, this is getting passed through, let us say, second order nonlinearity. So f0 and 2f0, if you let us say you pass in two sinusoids, one at f0, one at 2f0, and square it, what are the tones you get? No, yeah, something else. You get 3f0 also. These two will beat. The cross will give you 3f0. So finally, what can you say? What are the frequencies will present here? You will actually get all harmonics. Okay. So you shouldn't be surprised if you find that although your amplifier has only, let us say, second order distortion, you put it in feedback, you will have all harmonics, but of course the strengths of them will be very small, because if you have a large loop gain, then negative feedback loop will suppress it. Okay, that is something to note, right? Cool. So now let's actually, yeah. So bottom line, if you want to reduce the effect of nonlinearity, one go-to technique is using negative feedback.